This is Science Max, Experiments at Large. Science Max! Today we're moving air. We're moving it through a tube to make a Stomp rocket, vacuuming it out, turning it into a vortex, and taking it with us underwater. All on this episode of Science Max, Experiments at Large. That was amazing! Greetings, Science Maximites. My name is Phil, and it's moving day today on Science Max Experiments at Large. Let's see, where do I put this? This is probably a good spot. Today, we are moving air. You probably don't think that moving air will have a huge effect, but you'd be surprised what you can do by just moving air. But don't worry, we're not just gonna move the air around in boxes. We are going to build a rocket! And this rocket uses the science of stomping on something with your foot. This is a Stomp rocket, and it works by stomping on this plastic bottle, and air shoots through this tube and pushes the rocket up into the sky. And here is how you can build one of your very own. And remember, if I go too fast, don't worry. All of the steps are on the website, so you can follow along at your own speed. All you need is a 2-liter plastic bottle, 3 kinds of tape: electrical tape, duct tape, and science tape. Science tape is just the same as invisible tape, but I use this kind of tape for science. Then you want some plumber's tubing and some construction paper to make your actual rocket. First, you want to take your plumber's tubing and cut it into 3 lengths. And when I say you, I mean an adult, because you need to use a saw. So you saw it up into a long piece, a short piece, and an elbow piece. We want to make a long tube at the top, and then we also want to make a tube at the bottom so we can attach our 2-liter bottle to. And there we go. Ta-da! Ready to go. But of course, it doesn't stay up, so we have to attach it to a base. And it will look like this. And you see, it's been attached with duct tape here, and I've used electrical tape, and I've wrapped that part around there. Now, building the rocket. Wrap the paper around the tube and tape it with your science tape. Tape the top closed so no air escapes. Then cut a semicircle to make the nose cone, and 3 hoops for thrusters, and tape them to the bottom. There you go. The rocket fits on the tube just like that, and when you stomp on this bottle, it launches. But here's the most important part. The one most important rule of launching rockets. You shoot rockets outside. Come on. Once you get outside to a nice open area, and you bring your safety glasses with you, all you need to do to make the Stomp rocket work is, of course, stomp on it. You ready? Here we go. 3, 2, 1. Whoa! You see that? That was amazing. Okay, so this is where we're gonna start with the Stomp rocket. I'm gonna meet Chris from Logic's Academy, and he's gonna help me max it out. In fact, he's probably at Science Max headquarters already. I should get over there. Okay, where's the... Oh, there it is. Okay.
How you doing?
It's good to see you.
You too.
Chris is from Logic's Academy, and you guys do in-class robotics workshops, right?
That's right, we do.
Great. Well, I was hoping I could get your expertise to help me max out the Stomp rocket.
Yeah, Logix makes one of these. I totally think I can help you with that.
Fantastic. So it works great. I just want to make it bigger, better, more maxed out.
First off, we can start by making this pipe a little bit bigger. So a larger pipe, more airflow, bigger launch.
Okay, let's do it. Cool. Moving air isn't that hard, right? I mean, air is super light. How hard can it be to move? Well, here's an experiment you can do that lets you measure how hard it is to move air. So what I'm gonna do is I'm gonna hit the ruler with the broom. It's gonna go over there. I hit it, and it moved, no problem. So we're gonna do it again, except I'm gonna add just a couple pieces of newspaper. All right, ready? Aha, the ruler broke, because this time I wasn't just moving the ruler, I wasn't just moving the ruler and the newspaper, I had to move the ruler, the newspaper, and all of the air that was on top of the newspaper. And that resistance was enough to break the ruler. Pretty good experiment, right? Let's max it out. I've got more table space, I've got a piece of lumber, and instead of a newspaper, I have a tarp. Now the tarp is very light. It is not the weight of the tarp that is going to be the difference. It is how much air I need to move when I hit this piece of lumber. And I've got a Science Max hammer. So first of all, you're not gonna try this at home, right? Deal? Okay, deal. No trying this at home. Okay, here we go. Moving air, test 2.0. It broke, and it didn't even move. Did you see that? I wonder if we can max this out even more. 2x4, which is much bigger than the piece of wood we used last time, and a sledgehammer. Here we go, moving air experiment 3.0. Yeah, science. Whoa. So I've joined Chris from Logix Academy, and we are maxing out our Stomp rocket. To do that, we're gonna use
Larger pipe, more airflow, bigger launch.
The theory is that moving a larger volume of air through wider pipes will make our rocket work even better. So we get to work. This version is built exactly the same. We cut and attach the pipes, a long piece, an elbow, and a short piece, then secure them all down. We attach the plastic water bottle and tape it so it's airtight. And then the only thing to do is make a new rocket that fits over the larger pipe. Ready to try it?
I'm ready to try it.
All right, let's do it.
Let's go.
1, 2, 3, go! That was amazing! In the end, though it worked, it wasn't much better than the smaller rocket. I think we could still do better, right?
Oh, yeah.
This is Science Max, not Science Medium. Right, okay, let's go back to Science Max headquarters. Vacuum sealing. That's what you call it when you take all of the air out of something, often a bag, to seal in the freshness of food. I will demonstrate using this Science Max banana. 100% banana, but with added science.
Not all bananas contain science.
Here's how you can do it at home. Put your food in a bag, seal it most of the way, because we have to take out the air from the bag. And we will do that with a straw. Put a straw inside the bag, and then suck the air out of the bag, and then seal it at the very last second. There, a vacuum sealed banana. Now I know it's kind of hard to see that it's been vacuum sealed because bananas don't really crush much when you take the air out. So I like to use stuff that has a lot of air in it to begin with. In fact, there are special bags that are specifically for vacuum sealing that are supposed to store big and bulky items that have a lot of air in them, like this pillow. See this nozzle right here? It's designed to be used with a vacuum. So, what you do is you put the vacuum on this nozzle, open it up, and then you turn the vacuum on. Oh. The vacuum is sucking all the air out of the bag, just like we did with the banana. But because the pillow is full of air as well, it starts to shrink and shrink. Then you pull off the vacuum and you tie the seal off, and, all right. And ta-da! A vacuum sealed pillow. Okay, let's max it out. What could possibly be more maxed out than a vacuum sealed pillow? Vacuum sealed fill. Okay, I put plastic bags against the door and then sealed the edges with duct tape. And of course, I didn't put any plastic over my head because you never put your head in a plastic bag, right? Well, let's see if vacuum sealed fill, it works. Whoa. Hey, it's working! Haha! The vacuum sucks all the air from the bag, which seals the bag and me in it to the wall. That means I should be able to knock this milk crate out from under me.
Air pressure, or the lack of air pressure, is keeping me sealed to the door.
I'm completely suspended! Uh-oh. I shouldn't have done that.
Nope.
So our larger version of the Stomp rocket worked, but it didn't go as high as the first version. Chris and I see how we can improve the design.
The larger pipe and the larger rocket works really well.
It does work really well. I am afraid, though, that the larger pipe means that the same amount of air is flowing slower out the nozzle than it did before.
Oh, so because we're moving only this much air, it's not gonna go as fast because this is a bigger tube.
We need a bigger volume over here to match our larger
So a
nozzle.
bigger bottle.
That's right.
I got a bigger bottle right here. Ha-ha! Bigger bottle! So hold that, and then all we have to do is tape the bigger bottle
I'm not sure
on.
if that's gonna...
Yeah, like this.
Still, though, I'm afraid...
Yeah,
a
so
little
then
bit.
all I need to do is tape it on.
Chris and I attach a larger bottle to our tube. We just need some risers to adjust the height, then we tape it on and we're good to go. Everything else, including the rocket, stays the same.
I still don't understand how you're gonna step on this one. It's just too stiff.
I have a plan. Ha 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 ha! Sledgehammer! You ready?
Yeah, I'm ready.
Okay. 1, 2, 3! It blew the top off the rocket.
Right off
It
the
also
top.
blew the bottom.
Looks like it's a bit rigid to change its volume so quickly.
So it's kind of a one-time use thing, huh?
I think so.
So why don't we try increasing the volume? Even bigger tube,
Yeah.
even bigger container.
What's bigger than a... That's the biggest bottle they make.
What else holds air?
What about an air mattress?
Do you think we could use an air mattress?
I think we could, yeah, a really big air mattress.
Oh, totally. High five. I love that idea. Moving air is a lot of fun, especially if you use one of these, a Vortex cannon. They're pretty impressive and they use some pretty amazing science. I'll show you how to build one. It's pretty simple. All you need is a plastic cup. You want a balloon, something round, an elastic, scissors or a craft knife, and a pen. Here's what you do. Take your balloon and cut it just where it gets wide. You take the mouth of the cup right there, and you have to stretch the balloon over the top. And then you want to put an elastic around it, keep it in place. And this now is a surface on the top, and that's what you're going to use to pull back and create your burst of air. But of course, the air's not going to go anywhere until you make a hole in the bottom. So here's what you do. You take your round thing and draw a circle, and take your craft knife or a scissors and an adult and get them to help you cut out a hole. And when you pull back on the balloon, a burst of air comes through the hole. But the air has an interesting shape. Now, I know what you're thinking. You're thinking, Phil, air is invisible. You can't tell what shape it is. Well, I can show you. Come on. This is my maxed out Vortex cannon. It's made out of a garbage can. I've got a hole in here, and this is a shower curtain with a ball that I can get a grip on and pull. And then it shoots forward like this. Now it makes a big puff of air, but again, the air is invisible, so we don't know what shape it is, but I can help with that because I've got this, a fog machine. I fill the inside of the garbage can so we can see what the air is doing when I fire the Vortex cannon. Okay, come on over here. Ready? Whoa! Okay, ready? Check it out.
The Vortex cannon shapes the air into a ring, called a vortex.
It makes a ring. Well, actually sort of a donut.
Because of its shape, the air in a vortex can move much farther than air that doesn't have a shape.
Vortex cannon. Air that has a shape goes a lot further than air that doesn't have a shape. And it's also way more fun. Woohoo! Little to the left from load it. Okay, now that's too far left. I don't know what you think. Oh, hey, I don't suppose you're going on vacation anytime soon. Well, if you haven't decided where, may I suggest underwater. But don't forget to pack the most important thing when you go. Hat? Nah. Ukulele? Nah, forget about it. Rubber chicken? No. Sunscreen? Forget about it. Teddy? No, if you're going underwater, the most important thing you gotta pack is air. You see, human beings have been coming up with ways to go underwater for a long time, but the thing is, you gotta bring air with you because, you know, breathing is good. Check this out. It's a diving bell. One of the first ways humans used to be able to take air with them when they went underwater. You see, it's a big, heavy bell, and it's lowered from a ship above on a rope. And when it gets lowered into the water, it traps a bubble of air underneath. So you can swim around underwater, but then when you need to breathe again, you don't have to go all the way back up. You just pop under the bell and take another breath. Bells like this were actually much bigger when they used to use them for diving to hold more air. Huh? Ring-a-ding-ding. What do you think? You want this? No? It's okay. I got something else. Hold on. Check this out. It's an old-timey diving suit. Air is pumped in through these hoses here, which means the diver has a constant supply of air, which means he can stay underwater longer. What do you think? No? Okay, hold on. I got something else. Yeah. This is it. The ultimate in bringing air with you. The scuba suit. This tank holds compressed air, which means it can carry a lot of air with you, which means you can stay underwater for longer. So I'll tell you what, I'll wrap up all three things. What do you say? Yeah? You'll take them? Okay, great. Let me just wrap them up for you. Come on, Teddy, let's go find the bag.
So our large Stomp rocket hasn't worked perfectly. A small bottle didn't move enough air, but our larger bottle was too rigid to stomp. And when I used a sledgehammer, it was so sudden the bottle broke and also blew apart the rocket. Chris and I need a large container of air that is soft enough to change its shape easily. So here's the current plan. An even larger pipe, an even larger rocket, and we use an air mattress. We make 2 holes in the air mattress, one to fill it up with a leaf blower, and the other hole to go out the tube to the rocket. Since an air mattress holds lots of air and is very easy to change the shape by jumping on it, we figure it'll be a great way to get lots of air through the tube to launch our rocket.
Okay, let's do it.
Let's do it.
All right, we're gonna go 1, 2, 3, jump, right?
Okay, yeah.
1, 2, 3.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello! Welcome to Cooking with Science. I'm Buster Beaker. Whenever friends come over, I like to make my famous potato chip recipe. And look at this bag of potato chips. Quite large, there must be a lot of potato chips in here, right? Well, let's open it. What? This potato chip bag is mostly air. Why do potato chip bags have so much air? Well, to tell you the answer to that, I have to tell you the story of 2 bags of potato chips. Here they are. This one full of air, and this bag of potato chips, there's not much air in it at all. Why don't they make them like this? Well, let's find out. First thing that happens is the potato chip bags come off the conveyor belt at the potato chip factory where they get packed into a crate. Here's a crate here. So let's really stuff them in. And then the crate gets boxed up and shipped off to the store. Oh, it's a bumpy ride to the store today. Now we're at the store, and then you come along. Bags of potato chips. What else should I buy today? Oh, I know. How about a cantaloupe? Very nice. Some apples, yes? And take it home, walk along, and you get to the kitchen, you have a choice. This bag of potato chips, where all the potato chips are light and fluffy, or this bag of potato chips, which is not exciting at all. And that's why potato chip bags have so much air, to protect the potato chips from getting crushed. Speaking of potato chips, time to get back to my recipe. What is it? It's potato chip soup. Well, I'm Buster Beaker, and thanks for joining me on Cooking with Science. Perhaps a little bit more cooking.
Okay, so where were we? Oh, right, our maxed out rocket. A much larger pipe, a large air mattress, and the largest rocket yet. Let's see how it goes.
1, 2, 3, jump. 1, 2, 3. Yeah! There he goes. All right, let's do it again.
Okay.
1, 2, 3.
It works amazingly well. The large volume of air Chris and I can move by both jumping on the air mattress gets transferred through the large pipe, and even though it's a giant rocket, it sails higher than any other version.
That was great.
That was amazing. All right, there you go. Science Max, experiments at large, moving a lot of air.
That has to be the biggest stomp rocket ever.
Biggest stomp rocket ever. Let's do it again.
Okay.
Okay.
Science Max! This episode is all about chemical reactions.
Nom nom nom. Nom nom nom. Nom nom nom. Nom nom delicious.
Reactions to make things fly, to make things glow, to make things pop, and to make things fly.
That works.
Wait, did I mention the flying? I'm sure I did, but I'm mentioning it again because it's awesome. All on this episode of Science Max, Experiments at Large. Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, Stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means, because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. Come on, let's max it out. So first, I need an expert to help me. Lisa from Logix Academy, of course. Logix Academy people have helped me launch all the rockets on Science Max. This is gonna be great. I'm gonna get my helmet first. Okay, let's launch some rockets! Let's go! Whoa, wow, it's really dark in this room. I can't see anything.
Bill?
Lisa?
Bill?
Lisa?
Bill?
Where did this come from?
I guess the portal's malfunctioning. Hey, Lisa!
Hi!
From Logix Academy, great to have you here.
Great to be here.
Let's put this over there. We are here to max out the chemistry rocket!
Ooh, what is that?
It's just a small plastic container. But when we put an antacid tablet in there and some water,
Ah, we get a chemical reaction.
we get a chemical reaction. And so that's what creates the pressure. And then that pops the lid off and we get a little rocket.
Kaboom!
But now we're going to max it out. Get a bigger container and more.
Wait.
What?
How about if we launch a whole bunch of them?
Ooh, so we just get a lot of the small one and we launch them all at the same time.
Exactly.
Okay, great. So we just need a whole bunch of these and a whole bunch of.
And a whole bunch of science antacid.
Yeah, well, that's okay. I get them both in bulk. Come on, let's go put it together. I'm an acid, and I'm a base, and we are enemies. Whoa, well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons.
You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react.
Whoa. That is until water gets involved. Once you have water, acids and bases react. Here, take some protons. All your bases belong to us. Here you go. Take some protons. I don't need more. I want more. I want more protons. Here.
Water is a solvent, allowing the chemical reactions to take place.
Depending on the strength of the acids and bases, that reaction can be mild.
Would you like a proton?
Oh, no, really, I could.
Please take it.
Oh, well, thank you. That's very generous.
Have another.
No, perhaps, maybe I will.
Here's one.
Okay, maybe just one. But if the acids and bases are strong, the chemical reaction can be really extreme.
This is what's going on in the antacid tablet, and why, without water, nothing happens.
Oh, water!
Water?
Come
on! What'd you do?
What?
And that's the last one.
Lisa and I are maxing out our chemical-powered rocket, not by making it bigger, but by making more of them. How many more?
400 caps all glued down, 400 antacid tablets or part of,
Yep.
all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down.
We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on.
Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flip the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah.
Oh my goodness!
It's good luck if you catch one.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Okay. So let's go and we'll clean
All
this
right.
up afterwards.
Yeah,
Okay.
let's do it.
Okay, let it go. Whoa. Whoa. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex.
So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it, that separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready? Go! Science! Our first attempt to max out our chemical rocket was 400 plastic containers. Oh yeah. That worked well, but now it's time to make the container larger. Whoa! Giant maxed out chemistry rocket canister. I have a big plastic container with a groovy lid that sits there on airtight, which is great.
And I have a giant jar of antacid.
How many? It was like 60 antacid tablets or something?
At least.
This works exactly the same as our smaller containers. We dump the antacid in, seal the lid airtight, then flip it over. And now would be a good time to mention not to try this at home. Okay, it's not gonna take long. All right, so that was the canister version. Now we need the pop bottle version, the
Yes.
rocket version.
Yes.
Okay, let's go make that.
Let's do it.
Okay. This is a light stick. It creates light using a chemical reaction. There's a liquid chemical inside and also a glass container that holds another chemical. When you bend a light stick, you break open the container and the 2 chemicals mix, creating light. There you go, light sticks, chemical reaction. And yes, of course we're gonna max it out. This is a whole bunch of the 2 chemicals in a light stick. Let's max it out. So how does a chemical reaction produce light? Well, a lot of chemical reactions produce energy. You might think of a chemical reaction producing heat. Well, heat is a kind of energy. This chemical reaction also produces energy, just energy in the form of light. It's just a different kind of energy. Whoa, maxed out light stick! And now for a Science Max quiz. Chemical change or not? What's a chemical change? Well, let's demonstrate. Look at this. It's a happy little molecule of iron. And here's another molecule of oxygen. If they were to have a chemical change, they would react and form different molecules. Look, it's a molecule of rust. Rust is a different chemical than either iron or oxygen. It's a chemical change. Now, if these molecules mixed and did not change, then it's not a chemical change, it's a physical change. Sometimes it's hard to tell if it's a chemical change just by looking, but asking what kind of change it is leads to good science. So let's look at some examples. Vinegar and baking soda. Is it a chemical change? Yes. Vinegar and baking soda react to form different chemicals. Sodium acetate, that's the white stuff that's left over, and carbon dioxide, which makes the bubbles. How about a nucleation fountain with Diet Cola and mints? Haha! A lot of people think that's a chemical change, but it's not. The mints cause carbonation, the bubbles, to escape faster. But in the end, you still have cola and mints, no new chemicals. And without the carbonation, nothing happens. So it's a physical change. Take a guess at this one. Glow stick chemicals. Well, producing light or heat is usually a sign of a chemical change. How about mixing sugar and water to make a sugar pop? That's a physical change. You start with sugar and water, you mix them, and when you have a sugar pop, what chemicals are you left with? Well, sugar and water. So, no chemical change. It can be hard to tell sometimes, but whenever two things mix, think to yourself if it's a chemical change or a physical change. And now you know it's either one or the other. And that's the first step to good science. Thanks for playing our Science Max quiz. Our maxed out rocket worked great. Now to make it look more like a rocket.
So we have a mesh bag here to put the antacid in.
Right.
And we have some paper clips attached to it.
And what are the paper clips for?
Well, Phil, we have a magnet.
Ah.
And so the magnet sticks to the paper clip.
And so that's what we have here. You see, the bag is full of the antacid tablets, which we put through the mouth of the bottle, and the magnet is holding the paper clips on the other side of the plastic. So we can sort of move it along. So we can start with the bag over here where the water's down there, but now we attach the launcher like so. All this effort is to keep the reaction from happening until the bottle's on the launcher and we're ready to go. And then, as we pull the bottle over, we bring the bag up this side, and there, the water and the antacid have never touched.
No reaction.
All you need to do now is we pull this magnet away, and the bag will fall into the water, and then we will have the launcher down here, and we pull the release, and the rocket will go. We add some weight to the launcher to help keep it in place. Okay, right, wait, glasses.
Safety first.
Okay, ready? And then we pull the string with the magnet. That drops the bag of antacid tablets in the water and starts the chemical reaction. Because we have a latch holding the bottle down, we can wait until the chemical reaction happens fully. And there's a lot of gas pressure in the rocket before...
Three, two, one, launch! Woo! That worked.
Yeah, I had hit the ceiling. I think we need to do this outside.
Yeah, I think we definitely have to do it outside.
All right, totally great. Weird. Anyway, I was saying we should put 3 or 4 of... 3, 2, 1, go! There it is. Yeah! We tried it outside and it worked great. The only thing left was to max it out even more. So, larger chamber?
Yep, more antacid.
More antacid, more air, more water.
Absolutely.
Bigger rocket. Okay, so you know what? I know how to splice 2 bottles together, and we can increase the size of the chamber. This is sodium acetate. How do you get sodium acetate? Well, when you do a vinegar and baking soda reaction, what you have left, once the reaction is finished, is sodium acetate. It's a crystal, and you can do something fun with it that may seem familiar. You make a supersaturated solution of sodium acetate by heating water and dissolving as much as you can, and then when it cools, you can get the crystals to reform. Now, if you did this with sugar, you could make a sugar pop, which we've done before. If you do it with salt, you could make a salt pop, which is less appealing. And if you do it with sodium acetate, you can do this. Just like with the sugar pop, all it needs is a seed crystal to get the crystals to reform. But unlike sugar, which takes a few days, sodium acetate recrystallizes right before your eyes. Because we heated the water, it allowed more crystals to dissolve in it. Ooh. But then it cooled down afterward. There's more crystals sitting around in this water than there should be at this temperature. They want to turn back into crystals, and all they need is something to start them going. I've colored this one green because, I don't know, science. Maybe it'll look cool. A tiny crystal on the end of the stick is all we need to start the reaction happening. Whoa! Wow. And there you go, sodium acetate. That one wasn't done yet. we've gone from small containers,
Oh, yeah.
to a large container, to a rocket.
Yeah!
So what's next?
Super maxed out rocket!
12 2-liter bottles all spliced together to give us a very large chamber to build up pressure with.
So the chamber is all the same. So it's all one big hollow tube. And now we're gonna fire it off. Let's go!
Let's do it.
Awesome rocket! Yeah!
Lisa and I follow the same procedure as before. We use a bag of antacid tablets held up inside the rocket with a magnet. And once it's sealed on the launcher, we pull it off, let the antacid mix with the water, let the chemical reaction happen for a while to produce enough gas pressure, and then we fire it.
Okay, here we go. 3, 2, 1, go!
Oh my God!
That is the highest I think
Wow.
we've ever shot a rocket on Science Max.
That's amazing.
Well done. Chemical reaction rocket. Thank you very much for joining us on Science Max Experiments at Large. We should build another rocket because
I
that
think
one is probably broken.
That's done.
Okay, let's go.
Let's do it.
All right, so this time I think what we should need to do is... Oh no, it's nothing but garbage cans in there. We gotta turn the portal off. Come on, we gotta get... Science Max! 3, 2, 1.
We're really under pressure during this episode of Science Max. Compressing a gas till it's pressurized is how we can do this, and this, and to a lesser degree, this.
Help, I'm being crushed by all this pressure.
Pressure, today on Science Max Experiments at Large.
Phil to Mission Control. Come in, Mission Control. This is Mission Control, Phil. We read you loud and clear. I would... Oh. Greetings, Science! Greetings, Science Maximites! Welcome to Science Max Experiments at Large. My name is Phil McCordick, and today we're gonna be building an air-powered rocket. Too difficult, you say? Nonsense, it's easy. It's not like it's rocket science. Hey, it is rocket science. Cool! Here's what you need. You need a bottle and a cork. Make sure that the cork fits nicely into the bottle, and then you need an air pump, because you can't have an air-powered rocket without air. And on this air pump, you need a pin, the special kind that you use to inflate basketballs or volleyballs or stuff like that. Now, what you want to do is push the pin through the cork. You might want an adult's help for this. Push it through until it goes through on the other side, and then make sure you get a good seal with the bottle. Now you're ready to launch your rocket with air pressure. But first, let's do a few other things. Take your cork and put it in a tripod launcher. You can make this out of pencils or anything you want, as long as it stands up nice and solidly. And then, of course, you want to decorate your bottle so it looks like a rocket. This is my rocket. Pretty good, right? So stick the bottle on the cork like before, like that. And then you stick the pin in the bottom. And what we're gonna do is we're gonna inflate the bottle with air pressure, and then it's gonna launch. Okay, here we go. You know, rocketry really isn't something you should do indoors. Come on.
Hey, this was supposed to be a field. What's going? Why are there? Oh, it's in my shoe.
Oh, this will do nicely. Now, don't forget to do this with an adult, and don't forget your safety glasses. Now set up the rocket in a nice big open area, and make sure it's pointed away from you. And then what you do is you pump the air pump. And it puts air into the rocket, which pushes down on the water, which will push down on the cork, until eventually... So be Science Maximites and come up with your own rocket design. Try different amounts of water, different fins, even a different size bottle. Try it for yourself and see if you can get one that goes higher than mine just did. How did I get in? I think it was this way.
Do you want step-by-step directions on how to build your own air-powered rocket? Well, don't worry. Everything you need is on our website.
All right, now it is time to max out our air-powered rocket. I've got Adam here. Hey, Adam.
Hey, Phil.
How you doing?
Good, how are you?
Good. Adam's from Logix Academy, and you guys go into schools and talk about science.
We do.
Fantastic. Do you guys do a air-powered rocket?
Yes, exactly.
Does it look like this one?
Looks exactly like that.
Oh, that's great. So how do we max this out?
So we want to add more pressure to this bottle to try to get it to launch a little bit higher.
More air.
More air.
Great, so what do we do?
So we're going to use one of these.
Ooh.
It's an air compressor.
Right, which works a lot like the bike pump, right?
Yeah, exactly.
Cool.
So we're going to have compressed air coming from here through this tube into underneath here.
Yeah.
And out that nozzle there, and you're going to put your bottle on top.
And out the nozzle
like
into
that.
the bottle, like that.
Yep, and now we want to be able to hold it in place. So we're going to have these little fingers here that are actually going to work to hold it until we want to let it go. So we're going to lock it in place.
Oh yeah, look at that. Totally locked.
Exactly.
And then what? How do we launch
Now,
it?
you're going to take this cord and go a safe distance away, and we are going to pull it.
And then we would pull it. Which one do you want to start with?
I think we should use this one here.
Okay, great. Now we put water in it, right?
Yep, you're gonna put water in there.
Why do we use water?
So the water is gonna act to push the rocket up into the air. The compressed air in here is gonna shoot the water out the back, and the water is gonna push on the rocket and make it launch. It's just to give it a little extra push.
How do I get it on there without spilling any water?
So just rest it next to the
Just go
launcher
fast?
there. Yeah, just go really fast.
Ooh.
There you go.
There we
Raise
go.
A little bit.
Haha. And then
Lock it in place.
locking it in place. There's no
Okay.
air pressure in the hose yet, right?
Not yet, no.
First, we have to spool out the launch cord. So the air compressor has the compressed air in it. It's ready to go.
Yep, it's all ready to go. We just need to connect the hoses.
Adam, I've noticed it's snowing a little bit. Do you think that's any reason why we should stop?
I don't think so.
No, the science must go on. Blast shields down. Connecting hoses.
When we connect the air hose, the pressure from the compressor travels down the line and into the bottle. You can see the bubbles of air going in. Those bubbles are carrying more air into the bottle, giving it more pressure.
Here we go. 3, 2, 1. All right, there's the rocket. Let's do it again. Launching in 3, 2, 1. Woo! Nice. Success.
Success.
Nice. So, small bottle, worked really well. How do we make it bigger? I know, bigger nose cone?
I think a bigger bottle.
Oh, bigger bottle, yeah, of course, that's easy. How about this empty water bottle that we have now?
That might work, except that the top here is too big. I don't think it'll fit on our launcher.
Oh yeah, so what should we use?
A 2-liter pop bottle might work a bit better because it'll be about the same size.
Oh, that's right, 2-liter pop bottles have the same opening as these small water bottles.
Exactly.
That's great. All right, let's make a couple rockets out of 2-liter pop bottles.
Awesome.
Pressure happens when you squeeze something or compress it. Solids do not compress very well. I will demonstrate. Solid? Is it compressing? No, okay. Liquids don't compress very well either. You can demonstrate this for yourself by getting a plastic water bottle and filling it right to the very top with water and putting on the cap and squeezing. You'll find that you can't really squeeze the bottle very much. But if you empty out half of the water, no, don't pour it on the floor, and then put the cap back on the bottle and try to squeeze it, you'll find that you can squeeze it a lot more. That's because gases compress much easier than solids or liquids. Here's what's going on. Say this container is, well, any container, and these magnets are air molecules. Now I'm gonna put the magnets in pole to pole so they repel each other and wanna stay a certain distance apart, just like air molecules do. There we go, a container at normal gas pressure. Now watch what happens when I add more gas molecules. They start to get squeezed together. And if I add more, the amount of space that each one gets is less and less. Now this container is under a lot of pressure. These molecules really want to escape through the top of the container, but they can't because I'm holding them down. If I took something like this plunger and I pushed them down even more, now they're really under pressure. They want to get out, but they can't because I'm holding them in. Now watch what happens when I let them go. They all pop out the top, and the container has returned to normal gas pressure. That's what happens when we put gas in a container like this one. These containers that hold compressed gas are made out of solid steel because you need something really strong or it might explode if you put too much gas pressure in it. That's why these are only filled up by professionals who know exactly how much pressure it can take. That is the power of pressure.
Our air-powered rocket was working pretty well, but there's always room to max it out. In order to do that, we need to understand how it works. First, we fill the bottle almost halfway with water, and then we add air to the bottle. The air pressure builds up, and the air presses down on the water. The rocket takes off when we pull on the release valve, which was blocking the opening of the bottle. Once that happens, the air pushes out the water. It's the water that gives us our thrust, so the water is very important. Once all the water is gone, the air escapes and the bottle returns to normal air pressure. But by that time, it's high in the sky. Now the plan is to use 2-liter bottles instead of regular water bottles to see if they work better.
Now we've made a few more rockets out of 2-liter bottles, and I'm gonna fill this one up with water, and we're going to fire it again and see what happens. Now, the idea is that these will work better because they have more volume, and more volume means we could possibly put more air pressure in. It's hard to know until you try it, of course. But the other reason why it might work better is 2-liter bottles generally hold carbonated beverages, which means they already have to be made a little stronger than regular water bottles because they have to hold in the carbonation, which is just like air pressure. All right, ready to go. Okay, here we go. You ready, Adam?
Yep.
Okay, blast shield down. Pressurize! 3, 2, 1. Let's do another one. And 3, 2, 1. Whoa! Wow! This is the superhero design rocket, which I'm very excited about. All right, Adam, it's going really well. But before we fire this next one, how can we make it bigger, better, and more awesome?
Get more pressure.
More pressure. How do we do that?
Well, we're firing at about 90 PSI right now.
PSI, pounds per square inch of pressure, right?
Yeah. So we could increase it.
We could increase it. So we're at 90 now. How high does the tank go?
Go to about 120.
120 PSI. Let's see what happens.
All right, let's do it.
Here we go. 90, 110, 120. Should we fire it?
Let's fire it.
Let's fire it. Here we go. 3, 2, 1. All right. Hey, actually, it worked okay. There's just a piece missing here, but I think the bottle is still okay.
Yeah.
So, 2-liter bottle, full pressure. I think we can still make something even better, even more maxed out. What if we used an even bigger bottle? You know the 5-liter ones that you see on a water cooler?
Yeah.
You think we can use one of those?
Definitely. I think we could use that. We need to change the mouthpiece size
Yes.
to fit our launchers.
Well, let's do it.
Do it.
Help, I'm being crushed by all this pressure. A whole kilogram is being pushed down on every square centimeter of my body. 103 kilopascals. Actually, 1 kilogram for every square centimeter on your body is the exact kind of pressure that you and I are under at all times every day. We don't notice it because we're used to it, but it sounds like a lot, doesn't it? Well, it is. Here's an experiment you can do with a plastic bottle. Say at room temperature, there are 10 million air molecules in here. Doesn't really matter how many, but we'll say there's 10 million at normal room temperature. What happens if I heat up the air inside this bottle? This is warm water. What I'm trying to do is heat up the air inside the bottle because the air molecules, when they get hotter, move faster and need more room. So the 10 million air molecules are starting to escape out the mouth of the bottle and reducing the number of air molecules inside. And now I take the bottle out and cap it. Because the air molecules heated up and speeded up, they needed more room. Now there's less of them in the bottle. There's about 4 million air molecules inside this bottle, but they're all hot air molecules and they have a higher pressure, and you don't notice it because the air out here isn't crushing the bottle. But watch what happens if I cool the air inside the bottle. This is ice water. So what's happening now is the molecules are slowing down and they need less space. So they need less room and they're being crushed by the pressure on the outside of the bottle. It has been crushed because the colder air molecules don't need the same kind of room as the hot air molecules. The room temperature air has crushed the bottle. The air inside has a lower pressure than the air outside. Pretty amazing. Even more amazing when we max it out. This is a steel drum. What we've done is we put some water in it and we're heating it up to boiling so there's nothing but hot air inside the drum. This is an airtight cap, which we use to seal the drum. And now we cool the drum off. Hey, Trevor, give me a hand. Ready? 1, 2, 3, you lift! That's good. This pool is filled with ice. What we're doing now is cooling off the steel drum, which will cool off the air inside it, which means eventually the air inside the steel drum will be a much lower pressure than the air outside the steel drum.
Because this steel drum has a lot more volume than a 2-liter pop bottle, it takes a lot longer for the air to cool down. The other thing to think about is that it's a steel drum. I could stand on it and it wouldn't even dent. But sure enough, after a few minutes...
Whoa! Check it out! The barrel has totally crushed. The low pressure air inside the barrel wasn't enough to withstand the force of the regular air pressure that you and I walk through every day. The air pressure all around us is enough to crush a steel drum. How cool is that?
Our air-powered rockets have been working really well, but we still want to go further. Since the 2-liter bottle worked better than the water bottle, we think increasing the size again might make it more awesome. So now the plan is to switch our 2-liter bottle with a 20-liter water cooler jug and make a rocket out of that. Because the launcher nozzle, which holds the bottle in place till we're ready to launch it, isn't going to fit the opening of this bigger jug, we've decided to use the cap that came with the jug. If we screw the cap on, it'll work sort of like the cork. The air pressure will press down on the water and keep pushing against the cap until the cap has a catastrophic failure, which is a very cool way of saying that eventually the cap will break and the bottle will shoot into the sky.
20-liter water cooler jug filled with some water. This is the cap that'll work sort of like the cork. We put the air pressure in there, the cap can't take it anymore, pops off, and the thing flies, hopefully. Let's find out. Okay, that looks good. There. Let's do this. Go for pressure! Uh-oh. Uh-oh. Oh, no. Hilarious! That worked pretty well. It sort of does that. I wonder if it's aerodynamic.
No.
No. So, what else can we do to make it even more maxed out?
I think we've used the 2-liter bottles that work really well.
The 2-liter bottles
Yeah.
are the best, right?
I think so.
So, what do we do?
We can probably stack them. We stack them on top of each other.
Yeah.
That work.
I like that. So we put a whole bunch of them together.
Yeah.
Tell you what, I'll do you one better. Why don't we use 3 stacks?
Awesome.
We'll use 3 stacks, 3 launchers
3 times the thrust, and we'll make a giant rocket out of 2-liter bottle.
Yeah, great idea.
High fives. Here we go. Gas molecules get further apart when you warm them up and closer together when you cool them down. So what happens if you keep cooling them down? Well, they turn into this. This is liquid nitrogen. Nitrogen makes up 78% of the air we breathe, but when you cool it down to minus 196 degrees Celsius, it turns into a liquid. It's boiling right now because at room temperature, nitrogen wants to be a gas. So the liquid nitrogen is turning into gaseous nitrogen, and all of the extra molecules are escaping through the top of the bottle. So what happens if I put a cap on the bottle? Right now, the liquid nitrogen is turning back into a gas, but because there's a cap on the bottle, the gas has nowhere to go. So the pressure is just gonna keep building and building until the plastic bottle can't contain it anymore, and it pops like a balloon. Science!
Our rockets have gone from small to bigger to even bigger. Now the plan is to use 3 2-liter bottles and create columns of them into a giant rocket. We pressurize them just like we did before, but with more thrust, it might work even better. Even if it doesn't work better, I'm pretty excited about this new plan.
Giant rocket! Giant rocket! You ready?
I'm ready.
Okay, blast shields down. Connecting hose. Dialing up pressure. Pressure is rising. It's bubbling. Bubbling. 100 PSI. Okay, stand by to fire. 3, 2, 1. Whoa! Woo! Whoa! Awesome! Yeah, let's go check it out. Well, there you have it. Rocket Science Max. Experiments at large. Well done. Nicely, nicely done. Do you think we could fire it again? Yeah, it looks like it needs some repairs, though.
Science Max! Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, experiments at large.
Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in 2 ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxidrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator. Feel the chill of the refrigerator.
All right!
And last but not least, the, Regurgitator!
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind this small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law.
no, there's,
For every action,
there's
there is
plenty
an
of time
equal
for this
and
later. We're not
opposite
doing
reaction.
this bit now. We're doing that bit in a minute, so we can. No, I said we're doing it later. We're doing it later. Here. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock car?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way.
So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so sorry. Oh, I thought what we would do is I would, in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go!
Let it go.
I did.
You did let it go.
I had to let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can, all right, so I don't know if that's safe to do that, so we'd have to build like a cage or
Yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's a
they
good
can hold the
idea.
tanks, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity, he gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet,
and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. Oh, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third...
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use a compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right. So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked!
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
More tanks, more force. You're gonna go faster forward, Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use two balls. I swing two balls up, and two balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls, and I think it's gonna work the same way. Let's find out. You throw one out, and yeah, it works the same. Okay, now let's try it with two balls. Okay, ready? Wait. And two balls, throw them out. And two balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh. Ah!
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do two things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube,
Yeah.
and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks, thanks, Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go
Or it goes
that
forward.
way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
Yeah! Woo! Uh-oh. Woo-hoo-hoo! That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law.